אם אני לא יודע, הוא יודע. אתה יודע מה אני יודע.
אני לא יודע מה אני יודע.
תגיד, עשית את
התשובה ששלח, שימו את זה בפנים. בשאלה שלמה, בשאלה אחת, אני קופי פיס, פלוס
כן, לא הבנתי.
אני לא מתלונן.
לא הבנתי, אני פספסתי או שלא עלה?
לא עלה, ואני לא מתלונן. אין תלונות.
טוב, מה נשאר לי? מה נשאר לי? תודה, נתונים.
דיברנו על שפות עם אלי בבקעים.
עשיתי, אבל לא היינו מבחנים. כי היה לך חפיפה בשנה.
זה גם בשם הבאים.
הם איתך ככה דלת, הם לא קשים.
אחי, אתה יודע כמה לא ספר קשה. שבא לך, יש לך עשיתי כל השיעורים.
אלי מאז הוא הפעם
עשינו אלי.
אמרתי לך שזה לא אני לא הבנתי בהתחלה.
Good morning, everybody. We will continue our treatment of the canonical ensemble. I remind you where we stopped. So first of all, for microcanonical ensemble, we assume the following, that the energy is constant. This constant energy implies that we have a very harsh constraint in our system, and every problem becomes a hard combinatorial problem because many constituents have to satisfy this extremely harsh constraint. On the other hand, what we've done in the canonical ensemble, we get rid of this hard constraint, and we said that canonical ensemble, we said E is not constant. Our system can exchange energy with the reservoir. So this is our system. This is our heat bath reservoir. And the prominent thing about the canonical ensemble is that the temperature is constant. So constant temperature. What this implies is that A, we don't have a very harsh constraint. That can sound about a little bit of, well, that's good. Less constraints, usually less harder problem. But the energy is not constant, so how the energy is, well, we have to have a constant energy in our system. So the total energy in the heat bath and our system is constant, and we're using microcanonical ensemble for the whole system, and this is how we derive the equations for the probabilities to occupy each given state. So Fi equals to 1 over z e to the power minus beta ei, the moment that we have the energy of each state with energy ei, the probability to be in this state, to occupy state I, okay, where z is the partition function, and equals to the summation over all states e to the power minus beta. Okay. So we don't have constant energy, we have many energies. The system is never sitting in any given specific energy, right? It can transit from different energies accessible to it. What helps it to actually exchange the energy and modify its energy? The constant temperature. Due to the constant temperature, there are some fluctuations. So some of the energy gets out of the heat reservoir, some of the energy gets in. And this is why the energy is not conserved. And we now have probabilistic description of everything, microscopical probabilistic description. Find me the microscopical states, associate with each state the energy, and here you have the probabilities. How you connect it to the macroscopical description of thermodynamics, we have the following equations. F equals -1 over beta log of z. For example, we derived that the energy, which is the average energy, equals to minus d to d beta of log of z. Okay. So the moment that you compute the partition function, you're done. Okay. You know the probabilities, you know the free energy, you know the energy, everything is clear. So the road is always somehow to find a way to compute the partition function. Okay. So this is basically where we stop. Now we'll describe the only way how we know to compute the partition function. Except some examples where you have additional ways, but usually we always need to perform something that is called factorization. And now I'll describe to you, we've seen a specific example of this factorization. Now I'll describe to you what exactly this factorization means. Factorization in general words means we want to describe the system as if it is constituted by particles which are independent. Okay. So, factorization of the partition function. So, again, the partition function is z is a summation over all the possible states e to the power minus beta ei. If you don't remember, beta is 1 over k Boltzmann T. Okay. Now the next step is to write down this energy as a sum of many different energies, of different particles, or different entities that we have in our system. We say that the energy EI, it is what? So let's look on the different energies of the different particles. So we have particle 1, and it's going to be in state I. And we have a particle 2, and it's going to be in state I. And we have a particle 3, and it's also going to be in state I. Okay? And eventually we have a particle N, and it's going to be in state I. What exactly are particles? Who they are, what are their names, what are their colors, we don't care. Okay, so it's just a mathematical description of whatever we have. So the first assumption in our way to factorize anything is that we have to write our classes, write them in a red. So the assumption is that we have or we need to write our energy as a sum of energies of the different particles. Okay? So this is the first assumption. We can say Stas is always like that because the energy is extensive, but it doesn't have to be like that. Why? Because, well, maybe there is some sort of interactions between those particles. So maybe there are terms where there are multiplications between the energies of particle number 1 and particle number 3. So if you write this in this multiplicative way, it's not good enough. So this whole factorization approach says write down, find the particles, find the description such that I don't really care how you call those particles, but whatever you do, you write down your energy as a sum of different energies. And those energies are the energies of your particles, so-called particles. So this is the first assumption. The second assumption, so this is additivity. The second assumption is independence. All the energies E, E, J, I are independent. Okay, so the second assumption is independence. Second, independence. What I mean by this independence, and this is the second assumption, independence means that when I'm looking on my additive representation, I'm saying this energy can have whatever value, okay, and it doesn't really care, or it doesn't care at all, of what value is in E2, or what value is in E3, and what value is in En. So all the different particles have different energies, and those energies are independent of each other. One particle can have 37 kBoltzmann T, and En is going to have 6 kBoltzmann T. They don't care about each other at all. Okay. So this is the independence part. Two assumptions. Those two assumptions make everything as if we are looking on ideal gas. Ideal gas representation. Right? So what is an ideal gas? You put particles in a box. You say, what is the energy of the gas? You count all the kinetic energies of the particle. So your total energy is just the sum of the different kinetic energies of all the particles. This is assumption number one. Now, each of those different particles can have different energy. They do not interact with each other, so they have completely different energies. They don't care about each other. Okay, so this is assumption number two. This is why I call this, and not just I, this is the ideal gas representation. Now, it doesn't mean that we have indeed non-interacting particles. But the idea is, look on your system and find a way to represent it using new coordinates, using some associations between different molecules, whatever you want. But find a way to represent it as an ideal gas, additivity and independence. Okay. So what this factorization means. Eventually, we need to compute this function, right? This is z. Z is counting on all the possible states of my system, right? So I can write down what is a state. Questions? Yes.
EI is total.
So EI, what? This guy? So this is the total state. I will describe it exactly what it is now, right? So what is E1? E1, I'm looking on all the different energies. So E1, first of all, it is, I'm looking on the energy of the first particle at state I. So you're right, this is E total. Those are the different energies, okay, that correspond to, this is a naughty, I understand your question now. So what we will do, so write it down like this. E1 and E2 and E3 and En. So EI signifies the total energy of the system in state I. E of particle 1, upper script, superscript I is the energy of particle number 1 at state I, right? So I write it down. E I J number of the particle, identity of the particle.
Shouldn't be EJI.
It doesn't matter. But why does it matter if it's IJ or JI? The state of the system.
But what do you mean by state of
Exactly now, that's what I'm going to describe to you what exactly is state. So state for me, state I, is the energy, or is always defined by the energy. Right? So EI is the state number I. In state number I, what I mean by state, that I'm looking on the representation of all my system or all my particles, and I'm saying, well, red, I have E1, I, and I have EI, and I have EI. So I'm looking on combination or vector, if you like, of all the different energies of all the different particles. Okay. This is 2, this is 3, this is n. Okay. So the state EI is described when particle number 1 have energy E1I. When particle number 2 have energy E2I. When particle number 3 have energy E3I, etc., 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 etc. This is exactly my state. So I choose a vector of energies, all right? I put here specific numbers accessible to each and single particle, right? And I call this a state with a given specific energy, right? There can be some sort of degeneracy, right? So what I mean by degeneracy, so there can be 2 different states, right? So for example, I can switch E1I and E2Y. They can have exactly the same numbers. It's going to create exactly the same energy, but the 2 states will differ, right? Because the vectors are different. So the state is defined by a very specific vector of all the different energies of all the different particles. Right? The energy is just the sum of all of those different energies. So the degeneracy can come from different vectors that correspond to exactly the same sum. Right? Now, what I'm doing over here in constructing the partition function, z, is I'm taking the first state, which correspond to very specific set of numbers. I sum up all those numbers, okay, and I'm putting them into E1. Right. Then I choose the second state by some combinations of all the different numbers that I have over here, right? And I'm putting them all together, and I have E2, and this is E minus beta E2. E1 and E2 can be exactly the same number, all right? It can be exactly the same number, but I'm counting not on the different energies, I'm counting on the different states of the system, different representations of this vector that I wrote over here, okay? And I'm continuing the summation, and I'm summing over all the possible states. The I here is the energy of each state. There can be some sort of degeneracy. Okay, so I have to count over all the possible representations of this vector. Now, how I have to count depends, right? I have to count of all the possible values of E1, this guy, all the possible values of E2, all the possible values of E3, all the possible values of E4, etc., etc., etc. But what if I'll tell you the following thing? Let's write EI, or let's perform this summation, okay, Z, which is a summation over I e power minus beta EI. And I do the following thing. I'm summing over all the possible states, and instead of e to the power minus beta, I will write E1I plus E everything else. Everything else. What is E? E. E. The energy of all the particles except the first one. Okay. So I split my system into two. The first particle and the rest. Now, I have to sum up over all the possible representations of the different vectors. Now, what I'm suggesting to do is to perform the summation in the following way. Let's first sum up. Let's keep the E everything else constant. Okay? Let's choose a very specific representation of all of those guys. All right? And just modify the energies of the first particle. So what is going to happen? So it is Z equals to a summation all states of everybody else, everybody, or of EE, and a summation the states of the first particle. Can I do that? I have a total summation and I separate it into two sums. Let's count first the values of this guy and then afterwards count all the different values of that guy. So it is e to the power minus beta, and here I have E1, right? And can I have here I plus E of everybody else. I call it J. J is going to be upwards. So what happens? So I have all states of EE. Now look on this guy. This is just a sum. So I'm having e to the power minus beta E1 in state 1 plus E of everybody else in state I. Okay. Plus e to the power minus beta of E1 at state 2 plus the energy of everybody else, summing up over all the different states of I, plus e to the power minus beta of E1 state 3 plus E of everybody else state I, plus, etc. Right? So I'm just keeping this part constant and I'm just modifying the energy of the first particle over here. Okay, so if those are constants, so I will rewrite them in the following way. Summation of all states of everybody else. And here I have, this is an exponent of a sum. An exponent of a sum is just a multiplication. So I have e to the power minus beta E1 1 multiplied by e to the power minus beta of e everybody else I plus e to the power minus beta of e 1, 2, right? Multiplied by e to the power minus beta e of everybody else, state I, plus e to the power minus beta of e 1, 3, e to the everybody multiplied by e to the power minus beta of e of everybody else, state I, etc., etc., etc. Now notice something. This, because I'm keeping the state of everybody else constant, this is exactly like this and exactly like this. So I have a constant prefactor in this sum in the parentheses that multiplies each and every term in this very long sum that can actually be infinite. So I'm taking this constant prefactor out. I'll have e to the power minus beta energy of everybody else in some state I, and I'm summing up over all the possible states I. Now it is all states of everybody else, and here I have what I have, e to the power minus beta e1 1 plus e to the power minus beta e1 2 plus etc., etc. What is this sum?
It's a partition function of the individual particles.
Exactly. So this is Z1. It is a summation of, let's call it J, right? E to the power minus beta E1 J. So I'm looking at all the different states of one single particle, and I'm computing here the partition function of this one single particle. Okay. Now, it's as a constant. Due to my independence assumption, I can perform all those steps, and the Z1 is completely independent of all the different states of everybody else. Right? I counted over all possible values of E1 over here. They are completely independent of all the different other values. So this Z1 is not dependent on all the different other guys here. So what I obtained the following. Z equals to Z1 multiplied the summation of all states of everybody else, right? E to the power minus beta, everybody else, I. Great, right? So Z1, the partition function of the first particle. This is the partition function of everybody else, so I can write it down. Z equals to Z1 multiplied by Z of everybody else. Great. Now, let's perform this once again. Z of everybody else.
It's just Z2 times Z of everybody.
Exactly. I'm looking, what is Z of everybody else? I have to look on what is the E everybody else, I. It's represented by a vector. Now we start with E2, I, and E3, I, and E4, I. So all the different particles, E, N, I, all the different particles except particle number 1. Now I'm doing the same trick again. It's a one-trick pony. Right? You're doing this all over again. Oh, what is ZE? ZE, this is just summing all the different values of this E2, E3, E4, up to En. So, well, how we're going to sum it? Let's again sum only on the values of E2i, and that's it. So when I'm doing this, summation over the values of E2I gives me that Z of everybody else equals to Z2 of Z of everybody else, Okay? And what is Z2? Z2 is just a summation of I e to the power minus beta E2I. You just sum up over all the different values of E2. That's it. Now, I do it again. I look on the Z everybody else of everybody else. That's going to be exactly like this guy, just without the first part of the vector. And I do this trick again and again and again. Eventually, what we obtain? We obtain that Z is Z1 multiplied by Z2 multiplied by Z3 up to Zn. We look on each and different particle inside our system and we compute the partition function for this particle. Now, this is factorization. I remind you that factorization is the only trick that we're going to see in this class. And if you go to advanced statistical mechanics, probably over there too, most of the time, until we reach something that's called renormalization group. It's the only trick that we usually perform in order to compute the partition function. Partition function encodes in it all the information that we have to know to compute something, anything about the system. And the only way that we're going to learn how to compute the partition function is to performing this factorization trick. So all the physics is how we take a given system which looks complicated, which looks interacting, where the particles somehow depend on each other strongly, and how we are going to transform this complicated system into an ideal gas representation. That's the whole physics, always. Almost in any class that you learn. And it's also the same over here. Two caveats. Eventually, it's hard, really hard sometimes, to represent the system as an additive sum of different particles, and that those particles are independent. It's hard to find this representation. Okay, so this is what makes statistical mechanics hard sometimes. Now, another thing that we have over here is the following. Do you remember how we developed this canonical ensemble representation? We have a very strong assumption because otherwise it won't work. And the assumption was, we have a system, right? We have a system and we have a heat bath. And there was an exchange of energy between the system and the heat bath. Exchange of energy. And we have some constant T, which defined for macroscopic system. But the whole idea, everything over here, was that everything is macroscopical. All the descriptions, all the derivation, go back to your notebooks. You'll see that we always do something which is not really applicable to one system because we apply thermodynamics. It's applicable to large system, macroscopical system. And what I'm doing here with this factorization, I'm saying, well, forget about the macroscopical property of the system, focus on one single particle at a time, compute its partition function. What is a partition function for one single particle? Right? The partition function, it's a creature that we obtain by using macroscopical description of everything And now I'm saying, well, forget about it. Throw it out of the window. Look on one single particle, a microscopical description. So how can we do that? Is it okay? And the answer is yes. Because we haven't done anything wrong mathematically. And actually, when you're looking on a system like ideal gas, you don't care if it's one particle or many particles. Okay? You don't really care. As long as this math is correct, okay, you've done everything right. You haven't broke any assumptions. Although it's a little bit strange to compute a partition function of a single particle because all your assumptions were based on some sort of microscopical statistical physics, right? And large systems. But due to this independence, it's fine. Only due to the independence. Otherwise, you can, this procedure can survive. So it's fine to go into the microscopical description of each single particle, right? Each single particle, as long as the particles are independent. Now, usually, what you have is that the particles, not just independent, they have very, very similar properties. So when the properties of the particles are similar, Z is Z1 to the power n. Okay. That's it. Because this multiplication is just taking Z1 to the power of n, because Z1 equals to Z2 equals to Z3 equals to Zn. I want to discuss something that's called the Gibbs paradox. If you know what it is, forget about it for a while. If you don't know, it's fine. So for us, Z is just Z1 to the power of n, right? So now we are capable of computing almost any problem. Almost any problem. The procedure is for canonical ensemble. It's much more easier than the microcanonical ensemble. So the algorithm, if you remember, I wrote an algorithm how to solve problems in microcanonical ensemble. The algorithm for canonical algorithm for canonical ensemble is 1. Set constant T. Your temperature is set to something. You will maybe can modify it later, but set temperature. You can afterwards change it and modify it, but you set the temperature. 2. Write down the energy in additive form. Your energy at each given state, I, it is E1 I plus E2 I plus En I. 3, make sure that all the E I, J, E, K, L are independent. Are independent when K does not equals to I. Okay, so you have different particles, and you need that all the different energies of EI and EK are independent. Step number 3. Step number 4. Step number 4. And for each particle J, compute Z J equals a summation of all states e to the power minus beta e j I. Step number 5, z equals to j goes from 1 to n z over j. Step number 6, if you wish, you don't have to, you finished. Because the moment that you have the partition function, you're done. The goal is to compute the partition function. Out of the partition function, everything is known. Probabilities, the transition to free energy, everything is known the moment that you have written this guy over here. Now, in the 3-4 minutes that we've left, let's compute the same example that we've solved with the two-state model. Two-state model. Okay, so I remind you, we have a box of particles. All those particles are independent of each other. Okay, and for each particle, the energy spectrum is either 0 or epsilon. Okay. Those are the two states. Okay. So we want to find what we have found over there. I don't remember. We found the free energy, or we found the heat capacity. But let's for our purposes, we need to find the partition function, because out of the partition function you can compute whatever you like. Okay. So first of all, we set a constant t. T is some specific value constant. Write down the energy in additive form. Okay, this is easy because all the particles are independent and the total energy is just the sum of all the different particles. So E equals to E1 I plus E2 I plus etc. ENI. Great. Are they independent? Step number 3. They are independent by construction, right? So all the particles, it was provided to me that all the particles inside my box for this two-state model are completely independent. Great. So this is 1 done, 2 done, 3 done. For each particle, I compute Zj. Okay. Each particle, how many states does it have? 2, just 2 states, right? So if each particle have 2 states, Zj equals to e to the power minus beta. What is the first state? The energy of the first state is 0. So e to the power minus beta 0. What is the second state? E to the power minus beta epsilon. You're absolutely right. Now, all the different particles have exactly the same properties. So Z1 equals to Z2 equals to Z3 equals to Zn. This means that Z, the partition function, is just Z1 to the power n. Alright, so Z equals to what we have over here. It is 1 plus e to the power minus beta epsilon to the power of n. If you want to compute anything, right? If you want to compute anything, you go and say, well, the free energy is 1 minus 1 over beta log of z. In our case, f is going to be minus 1 over beta and log of 1 plus e to the power minus beta epsilon. You know everything that you need to know about, but that everyone needs to know about thermodynamical properties. You want to compute anything, you take the respective derivative of the free energy to whatever coordinate that you want. Here you're done. Okay. Easy peasy. We worked something like half an hour, a little bit more, for the two-state problem with all these Stirling approximations, etc., etc., etc. It was extremely long. Here it's extremely easy. But what is much more important, the microcanonical ensemble approach is not scalable. If I want to solve the same problem in microcanonical way, well, I'll have 0, epsilon 1, and epsilon 2, I'm in big trouble because the combinatorial problem of setting exactly all the different particles and all the different states is hard. Microcanonical is a hard approach. In our case, well, you added additional energy. Well, the only thing that I'm going to do is to modify this guy from epsilon to epsilon 2 and add an additional state in minus beta epsilon 2, and I'm done. That's it. That's the whole story. So it's, you add something a little bit more, the approach or the difficulty is almost exactly the same. Okay? Nothing changes. So this is the great advancement of the canonical ensemble. We're done for today. We'll continue to another interesting example of canonical ensemble tomorrow. I have a question for you before you go out free. The quiz is next week on Wednesday, right? Wednesday. So I got several emails from people that it's very, very hard for you to get up very early and arrive here at 8 a.m. My suggestion, after some discussions with the TAs maybe, is to move it to the lecture time on Tuesday at 12. And I'll have an additional lecture on some Wednesday morning where whoever cannot arrive in such early time. What do you say?
Yes.
Yes, there is a general agreement with that? Okay, so I'll try to speak with Nirit, and if you find, I'll speak to Nirit about that, and if we can find another classroom, because this classroom is going to be too small. You're around 120 students in the class registered. This class is about 110, and usually on the quiz, a lot more people arrive. So we will find another classroom. That's what we will do. All right, see you all tomorrow. כן.
השאלה הראשונה שדרשת את אי-תלות, דרשת את הפר...
כן, כולם בלתי תלויים מכולם, אחרת אי אפשר לעשות את הפר.
על כל האנרגיות.
על כל מצב ומצב.
אז פר מצב,
פר מצב, כן.
אז יכול להיות תלות אבל בין מצבים שונים?
בתוך החלקיק עצמו זה כבר משהו אחר. אבל בין החלקיקים האחרים אין תלות בכלל. אין תלות בכלל. כי אחרת הפקטוריזציה, הדבר הזה לא יהיה.
והדבר הנוסף?
תחשוב, זה תוצאה של סכימה. האם אני מצליח לעשות סכימה 1-1-1 או שלא? ברגע שיש לך איזה שהם אילוצים, נניח שהאנרגיות של הראשון, כשהאנרגיה של הראשון משתנה ל3, האנרגיה של השלישי חייבת להיות 2. ברגע שיש לך אילוצים כאלה, אתה לא מצליח לסכום. זה הכל, זה תוצאה של הסכימה.
זה נכון, עכשיו אני שואל נגיד, אם אבל עשינו את זה סכימה פר אנרגיה אחת, כאילו שבין שלב ל-I, ואני יש לי עדיין בין I ל-J, עדיין הסכימה תעבוד, לא?
לא. היא תעבוד רק אם התלות היא בתוך החלקיק עצמו. הוא תלוי בין המצבים של עצמו, משהו בסגנון.
אז אני יכול
אבל ברגע שהיא תלוי באחרים, אתה לא תצליח להוציא אותו.
הבנתי, אוקיי. והדבר הנוסף הוא, כאילו אני רואה בזה, אם יש את ה-E במינוס ואת ה-I, אז אני רואה ככל שהאנרגיה היא כאילו יורדת עולה ולא ברמת היסוד, אז אני חושב גם קל יותר. אבל למה זה לא כאילו, הייתי מצטער שזה אחד יותר, לא בשביל שזה תמיד יתכנס נגיד אם אני רוצה שמשהו.
למה לא יותר איתי? זה מה שקיבלנו.
כי כאילו, הרי יש ממש הסתברות הרבה יותר גדולה להיות, נגיד, שחלקיק ירצה להיות באנרגיה ממש...
אבל זה בטא. הבטא מסנכרן הזה, יש לך איזה טרייד-אוף בין הבטא לבין האי.
אבל זה יהיה פקטור...
תחשוב על זה בצורה כזאת, אם אתה רוצה לחשוב על זה בצורה יותר פשוטה, אז בגלל כל המכפלות זה איזשהו, צריכה להיות איזושהי פונקציה, אוקיי? שאנרגיה חלקי איזושהי אנרגיה אפקטיבית. היא אפקטיבית. אוקיי? כי אחרת יש לך פונקציה של אנרגיה מבחינת יחידות, זה אף פעם לא מסתדר. זה צריך להיות איזשהו מספר. אז האנרגיה האפקטיבית היחידה שיש לך זה קיבול פונקציה. סבבה? זהו. אתה יכול להגיד, רגע, אולי זה יהיה בריבוע, אבל זה לא יצא. אבל זה חייב להיות בולטמנטי, והדבר הכי פשוט זה פשוט תלות ליניארית בתוך אקספוננט. אבל תכל'ס זו תוצאה של ההנחות שלנו באמצע. אין... ברמה היסוד זה הכל מגיע מתוך זה שאמרנו, טוב, יש לנו אנטרופיה, שזה משהו, וזה גודל כפלי. מכל הגדלים הכפליים האלה יוצאת האקספוננט.
מה ששאלך לפי שלא היה, זה לא שם. זה טוב. אז איך תספיק לקרוא לסילבוס?
מה זה ההתאמות שלך? אתה אולי תכתוב לי אימייל כדי שאפשר לדבר פה ולהגיע לכולם על ההתאמות. זה לא מפריע לי, אבל בסדר, עדיף שתכתוב אימייל, זה ככה יותר אינטימי ולא הכל אפשר להתאים. תלוי מה ההתאמות שלך. אני אשתדל לעשות. תכתוב אימייל.
זה כאילו חשמל, המערכת של כאילו לפרוע לא בניתוח של הצבר הקנוני, אנחנו מרשים לאנרגיה להיות בכל מצב, אז אנחנו חושבים
לא, האנרגיה שאתה מחשב בסוף, נניח אתה תחשב היא בחזקה.
אם אני דוקא צד אני...
לא. מינוס D ל-D בטא, זה תוחלת. האנרגיה לא נשמרת. כשאתה מחשב איזושהי אנרגיה, או שאתה אומר אנרגיית מצב, זה משהו גודל קבוע, מוגדר על ידי המודל שלך, או שזה אנרגיית התוחלת, האנרגיה ממוצעת. זהו, אין אנרגיה. האנרגיה לא נשמרת, אז כשאתה אומר לי אנרגיה, אני אומר אנרגיה ממוצעת. כן, זה כל ההבדל. זה כל ההבדל, שבצבר מיקרו-קנוני, זה ככה פתחתי את השוק. צבר מיקרו-קנוני מתחיל מזה שהאנרגיה קבועה. צבר קנוני מתחיל מזה שהאנרגיה יכולה להשתנות במה שבא לך, אין שום אנרגיה.
שואלים פשוט ממש פשוט כאילו, לא מדברים על אנרגיה.
ככה פתחתי את השוק, מה שפתחתי את השוק, ככה פתחתי את השוק. כן. ברגע שרשמת את שני הדברים האלה, אמרנו שאתה ניגע זה רק עם חלקיקים אחרים, והאנרגיות שלך אולי לא אנרגיות קינטיות וכו', אבל עקרונית הטיפול הוא כמו בגלגל.
כשאני מסתכל על הזווית הזאת שבה...
זאת הדרך. לא, אתה החלטת אותה. נכון, בדרך כלל זה ייכנס לך לתוך ה-Z1. ה-Z1 יראה לך את הדברים הנוספים.
אני מנסה להבין למה אני לעשות את כל הדבר הזה.
כי אחרת אתה לא תצליח לחשב את הפרטישן פאנקשן. אנחנו מכירים כמה שיטות לחישוב הפרטישן פאנקשן. רמה עקרונית, או שלמודל ספציפית שיש איזושהי אינטראקציות, במספר מאוד קטן של מודלים אפשר לחשב את זה בצורה מדויקת, אוקיי? כשיש אינטראקציות. יש את השיטה שאנחנו לומדים, שיטה נוספת שהתפתחה בשנות ה-80, שנקראת רנורמליזיישן גרופ, חבורת הרנורמליזציה. לומדים את זה בסטטיסטיקה מתקדמת, זכו על זה פרס נובל ב-1990. לא נגיע לזה, זה חדש מדי.
גם שם כולם מדברים כל מי
לא, אני המציאו לי את זה.
לא, תראי, 14, אבל אני נמצאת בפרצון עושים, אני גם בכל
מה אני אעשה? לא הספקתי, מה אני אעשה? ברכות, לא הספקתי, מה אני שומע על פוקר, מה אני אעשה?
אני כבר לא מסתכל בחצי ימים של מה?
אני אחר כך מקבלת להעביר את זה ליסודות לא צריך. לוקחת 4, בסדר?
למה לא? השאלה אם יש לזה לו"ז אחר שרוצים להכניס
שאני לומדת ממנו ככה, סודר. אני לא רואה את זה שם מיליון. שהתקרת שלי עובדת כן, אני לא יודע, מה כאילו שקיפים של למה זה למה לא שבוע הבא אני באה לפיליפ. זהו. כאילו היה לי לחצות את כל מי זה? אבל סליחה, וואי. סליחה. מה? כאילו בול בזמן. דבר איתך אותה.